we present learning object states from actions via large language models. In this study, our goal is to achieve object state recognition by predicting the timings of where a specific object state is present in a video. We set this problem as a frame-wise multi-label classification task. Consider a scenario where an intact egg appears on the screen. This egg gets cracked and then whisked, while it remains raw throughout the entire scene. This object state recognition is essential for various domains such as cooking, assembly, and robotics, in order for the system to perform actions according to the state of objects. Despite its importance, this task faces significant challenges due to a lack of training data. Manual annotation of object states requires a lot of exhausting work, and it is vulnerable to the change of a vocabulary. Although previous works proposed a self-supervised method to learn from uncreated videos, it relies on strict constraints that specific object state change happens only once in a video. Additionally, the recent trend of learning vision language models from internet videos using raw narration has its limitations. This approach struggles with object states, as the narrations primarily mention actions and rarely provide detailed information about object states. To address this issue, we propose a novel approach that utilizes word knowledge of large language models to expand object state information, which is not explicitly told in the narration. We first extract action information from narration using LLMs and then infer object states based on action information. Our idea is based on observation that a sequence of past actions extracted from video narrations tells about when an object state appears and disappears. The relationship between actions and object states implicitly encoded in LLMs allows us to generate pseudo-object state labels to train a frame-wise object state classification model. Specifically, we propose a three-step framework to infer object state labels from narration. First, given a video that features a target object and the corresponding transcribed narrations, we extract a set of manipulation actions describing the actions related to target objects. Since the narration is long, we split it into blocks and feed them to LLMs. Next, for each primary action, we generated state descriptions which describe the resulting states caused or inferred by that specific action. In this step, we also feed the past state to keep track of it and better infer the new state. Finally, the accumulated list of inferred state descriptions is used to determine the presence of a specific object state at each time. We make sure to use the entire context of past state descriptions to accurately label the object state at a specific moment and suppress hallucination. The whole process yields object state descriptions and labels corresponding to each action. We also utilize VLMs to ensure that each video frame is aligned with the correct action and the corresponding object state description. First, we conduct action alignment. For each video frame, we take temporally close inferred actions and use VLM to infer the most plausible action, including an option that represents no action or other action is happening. If no action is happening, the video frame is not used for training. After we ensure that a certain action is taking place, we examine further to ensure that the corresponding object state description is true for that video frame. If it is true, we assign corresponding generated object state labels to the video frame. If not, the ambiguous labels are assigned and the video frame is not used for training. As a result, we obtain frame-wise object state pseudo-labels for each video. This pseudo-label occasionally includes ambiguous labels. The ambiguous label is either automatically assigned because no action is happening at the time, predicted by LLM because the state is not clear from the action information, or filtered by VLM because the action or state description is not aligned with the frame. We use these pseudo-labels to train context-aware multi-label classifiers. As for ambiguous labels, we don't compute the loss and don't backpropagate. However, we find that directly training the model from these sparse labels over time leads to incorrect context learning in the model. Therefore, we introduced a self-training strategy to mitigate the label sparsity problem. We train two classification models with and without context information, which will serve as teacher models. Then, we trained another set of models as student models, using weighted sum of teacher models' predictions as ground truth. The teacher models are also updated by copying the parameter of student models with momentum to ensure slow update. The two models with different context lengths have complementary natures in predicting object states, and thus the ensemble of these models' outputs is better aligned with ground truth. To evaluate our method, we collect multiple object state transition, MOST dataset. This dataset includes more than 150 minutes of videos with exhaustive object state annotations. There are 6 object categories and 10 state categories per object. Compared to the previous dataset for object state localization tasks, our dataset includes more complicated transition patterns between different states. We compare our method with strong zero-shot VLMs, which are trained based on raw image captions or video narrations. Our method significantly improves both fmax and mean average precision scores, demonstrating the effectiveness of learning from LLM-generated pseudo-labels. Here are the qualitative results. Please refer to our paper and website for more qualitative examples. Thank you for listening.